and then substituting the result into the other equation. So here are two equations. 4x plus y is equal to 9. 3x minus y is equal to 5. We will solve this by using substitution, but I want to first begin by showing you the equation of these two lines graphed so we can identify, again, the interpretation and meaning of what a solution to a system is. The first line is a line with positive slope. So this line, I suspect, is 3x minus y is equal to 5. And then the other line should be the 4x plus y is equal to 9. They seem to intersect in some point. If only I could see better, I think that might be the ordered pair 2, 1. Let's see if I can zoom in and see. It's 2, 1. That point lies on both lines. But again, we're lucky because those points are whole numbers. The x value is a whole number, the y value is a whole number. There wasn't a lot of estimating going on, which you really don't want to do. You want to have an exact answer. So we're going to do this by substitution, which again I suspect you know. You begin by solving one of the equations for one of the variables. I think that I might have more space for this on the next slide, so I'm going to scoot on over. We want to solve one of the equations for one of the variables. I don't remember the equations, so I need to go back and get them. 4x plus y is equal to 9. 4x plus y is equal to 9. And the other is 3x minus y is equal to 5. So we're going to solve one of the equations for one of the variables. I would tend to opt to solve equation 1 for y. Think about y for a second. I'm about to substitute the variable into the other equation. The easiest variable for me to solve for is y in the top equation. I can get y alone by simply subtracting 4x on both sides. Now we will substitute, we're on to step 2, substitute that expression into the other equation. So here's equation 1 solved for y. I'm now going to take 9 minus 4x and place it into equation 2 for the y. Equation 2 says 3x minus y is equal to 5. I'm going to replace y with 9 minus 4x. Please remember to put it in parentheses because you are replacing a single variable y with a two-term piece, 9 minus 4x. So please put it in parentheses because now you will need to distribute this negative through. That will give us 7x minus 9 is equal to 5. The good news about this now is you end up with an equation that has only x in it. Now for some reason my notes don't continue on to tell you what to do next, but I'm hoping that at least it's obvious considering that we only have one variable now. We can add 9 to both sides and get that 7x is equal to 14, divide both sides by 7, and we get that x is equal to 2. There is a third step. You have to solve for the other variable using any equation you prefer. Since the solution should work in the original equation 1 or the original equation 2 or the solved for y equation, you can use equation 1, equation 2, or the alternative of equation 1. It doesn't really matter which one you choose. Now, I will tell you that the easiest is this one. That's because I now know the value for x, it's 2. I can simply substitute that number 2 in for this x right here, giving me the value for y. So y equals 9 minus 4x. I know that x is 2. y will equal 9 minus 8, and we get that y is 1. Do you remember what the graph told us the solution would be? Let's go back and look. It said x would be 2 and y would be 1, which is exactly what we got by using substitution. Now, this is a lot of information about what we'll really be doing in section 2.2 because elimination or Gaussian elimination or the echelon method all use this information. So I'll give it to you briefly here just because we will use it later, but I'm not going to actually use it in this section. Two systems are equivalent if they have the same solution. So again, two systems are equivalent if they have the same solution. By performing certain operations, such as swapping the order of the equations, multiplying an equation by a constant, adding or subtracting two equations to one another, by doing any of those things to the system, we will obtain a different looking system, but one that has an equivalent solution. We can actually formalize this. There are three operations that lead to an equivalent system. The first is you can swap two equations. So swapping the order of two equations. This might sound nonsensical, but all it really means is if you have two equations that you are finding the solution to, one of the ways to find the solution is by graphing them. And then it doesn't matter the order in which you graph the two equations. So you are allowed to swap the order of the two equations and nothing bad happens. The other thing you are allowed to do, because these are equations, you can multiply or divide any equation by a non-zero constant. And again, that I hope makes sense, because if 2x plus y equals 5, you are allowed to do whatever you like to an equation, as long as you do the same thing to the left side and to the right side. The third one's a little bit kooky, but it's going to be the thing we use the most frequently. You can replace any equation in the system by the sum of the product, well, that's not, I think, quite the right word, by the sum of multiples of any two equations. We'll get to that in 2.2, so don't worry too much about really knowing what that means because we're not doing it in this section. Using these transformations leads to an equivalent system because each transformation can be reversed or undone, allowing us to return to the original system. Using these operations with two equations with two unknowns ends up being known as the elimination method. So the idea is to use these operations that we just saw to transform the original system into something that looks like this. But that's not really